Welcome to the 28th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to be talking about Chapter 22, Decoherence and Squeeze States. The image on the left is an image from an ion trap experiment that worked with a very large number of ions in a Penning trap. And this experiment was used to detect exactly how many phonons were excited in the center of mass mode and to actually determine the effective temperature of the center of mass mode. It's a very clever experiment, and we describe in detail how that works. Chapter 22, Decoherence and Squeezed States. We start the chapter off describing mixed states and density matrices. A mixed state is just a statistical distribution of pure states. It's not something that is particularly complicated, but that is a new wrinkle on the types of states that I can have in quantum mechanics. And as a result, we have to describe them using something called a density matrix as opposed to the states that we've been using before. Density matrices have certain kinds of properties. One of the properties that they have is that they get updated in a way that maps density matrices to density matrices, similar to the way that operators map vectors onto vectors. So they map state vectors to state vectors. The mapping of a density matrix to a density matrix is a little more complicated than the mapping of a vector to a vector, as you might suspect, because it's a matrix. And so we have to understand that mapping when we're working with density matrices. There are a number of very important kinds of mixed states. Thermal distribution, so if you say I have a quantum system at a particular temperature, that is actually a mixed state. So you need to understand mixed states if you want to look at problems that are quantum problems at some fixed temperature. There also are things called quantum channels. This is how density matrices get mapped to density matrices. And we look at the simplest kinds of quantum channels, those that act on a single degree of freedom, which is a quantum spin. Nevertheless, there's still a lot of them. They're still complicated. And so there's lots of interesting material that we get just by studying the quantum channels of a single spin. This leads us to the Lindblad master equation, which is an approximate way in which density matrices can be updated from one time to another time, and they do so by working with things called Krauss operators. So we discuss what Krauss operators are, how you determine what they are for your system, and so forth. Then we look at a real application, magnetic resonance. How does magnetic resonance work in the presence of decoherence? The two interesting experiments to look at there are Rabi oscillations and the Hahn spin echo experiment. Then we look at spin squeezing. That was an example of a problem that was looked at by using some exact approaches related to nice features of the Ising model. This is work that I did with a student for their undergraduate thesis. And there's lots of interesting results looking at spin squeezing. And it also is related to the work that we did with the Penning trap, which I showed you at the beginning on the first slide. And then we conclude the chapter by talking about the damped harmonic oscillator. It's a really interesting problem to look at, and when you think of it quantum mechanically and you think about things like uncertainty, there are a lot of subtleties and nuances that enter when you talk about a damped harmonic oscillator. So we have an opportunity to talk about that as well in this chapter. Hey guys, let's go browse through the chapter. All right, as you can see, I have a typo here. I used the same quote as I used in the previous chapter. That will, of course, get updated in the revised book. So the key about decoherence is that quantum systems always are in the presence of some kind of environment. Environment is essentially everything else that's around us that we don't know how to describe. And unfortunately, because interacting quantum systems interact with everything around them, the system will ultimately start to get entangled with the environment. Now, what we know is when we entangle with degrees of freedom that we don't measure, that gets rid of interference effects. And that process of entanglement that gets rid of interference effects is what decoherence is. So this is something that isn't mysterious. We've actually seen it already. And it just is something that is rather prevalent, so we need to be able to describe it with a mathematical formalism. We're required to describe things with mixed states and density matrices because you can't describe these kinds of entangled states when you integrate grade out the degrees of freedom that you do not take into account using pure quantum states. You need to have density matrices to describe them. So we talk about how you get density matrices, how you work with them, and what their properties are. They have some subtle properties to them, and one of their properties is particularly subtle. We discuss it and tell you about it, but we don't show you all the details about that property. It's called complete positivity, and it is kind of a difficult property to easily work with. There's a bit of formalism here. That's why you see a lot of equations. One of the things that's very important in working with density matrices is that you are able to do partial traces, because that's the way in which you integrate out the environment. An important state is the maximally mixed state. So we talk about what that maximally mixed state is. Then we get into thermal distributions. This is probably the most famous and most important mixed state that there is. We talk about how you generate it. Now, we're not talking about a full quantum statistical mechanics description, but we give you enough description that you can understand how that works. Next up are quantum channels. We talk about what a quantum channel is. There are a number of them. One of them is a depolarizing channel. We talk about how that works. We then talk about a dephasing channel. And there's an amplitude damping channel as well that we will talk about. That we talk about in the problems. There also are interesting techniques that arise when you're talking about decoherence and working with density matrices, and one of them is the so-called Stein-Spring dilation. We discuss how that works as well. Stein-Spring dilation brings us into Krauss operators, so we now talk about how Krauss operators work and what they are, and how you could, in principle, derive them from your full quantum system. In practice, most people don't do that because it's very difficult to do. We really don't know exactly how to do all the steps to do it. So instead, people postulate Krauss operators and see what the effects are of them. Once we have the Krauss operators, we can describe how a master equation works. A master equation is essentially the time evolution for a density matrix, and it's more complicated than the way that it works just for the time evolution of a state. So that's why it gets another name. It's called a master equation. Really cool equation. Sounds like it solves everything. Maybe it does. I don't know the origin of where a master equation comes from. You know, they're not something to be afraid of. They're just a little bit more complicated than the way that we were doing time evolution before. So it's not something that you should find too imposing. Then we go into great detail of how this works when you look at nuclear magnetic resonance of a single spin. And there are a number of different kinds of channels that you can look at applying to that. We use this to look at how Ramsey experiments work, but now the oscillations will decay due to the decoherence. We also talk about how the Hahn spin echo works. And then after that, we move into spin squeezing and spin phonon entanglement in ion traps. This is the protocol that is used for a spin squeezing experiment. We start with a state that is primarily having its spin oriented in the z direction. That would be something that is in, say, the maximal z component of spin. We then flip it into the xy plane. We apply the Hamiltonian onto it, which actually changes the state into a squeezed state. We then do some diagnostics on the squeezed state to properly orient it so that we can look at the part of the squeezed state that has the lowest uncertainty. And it's an interesting experiment to work with. What is particularly interesting is if we do this with an Ising model, we can actually work through all of the analytics exactly. And again, it uses our operators in order to do that. And it's pretty cool the way that that all fits together and how you can analyze this particularly complicated experiment. And this is the work that I did with an undergraduate for their thesis. And I'm showing you some of the images from the papers that we published based on that thesis. And then this is the experiment that I talked about in the penning trap. It's somewhat similar to the spin squeezing experiment, but a little bit different. And it allows us to essentially count the number of phonons that have been excited in each mode of the penning trap, at least for the modes that are at frequencies close to the center of mass frequency mode. It's pretty cool how that's done. And you can actually do high precision experiments that detect forces and other kinds of high precision experiments using this technique. I believe the claim was that it could measure some of the weakest forces present, like maybe zeptojoules or something like that. I don't remember all the details of exactly what the claims were about it, but it's a pretty remarkable device and remarkable experiment. So again, using our operated methods, we can describe that experiment, and it's kind of cool the way all of the stuff that we've been working on fits together. And then we have our last section, which is the damped simple harmonic oscillator. It's kind of nice the way that it fits together. This requires us to use a Lindblad equation that has what are so-called lamp shift operators as well. We hadn't talked about the lamp shift operators before. When you look at the evolution of it, it does exactly what a damped harmonic oscillator should. It gets oscillations that get damped out. It brings in some conundrums, though. What happens to uncertainty when the motion is damped out and the oscillator is no longer moving? I actually don't answer that for you in full detail. I leave that as a problem and something for you to think about. This is something that people have worked on in research. I wouldn't say that there is a clear answer to what comes out of that, but it is something that is interesting to think about, and think about what the quantum mechanical ramifications of that are. Well, that brings us to the end of chapter 22. Hey guys, let's do quantum right.